This is part 3 of nerve cells and nerve impulses. I think we were right in the middle, really, of talking about the electrical conduction that occurs down the axon, so the nerve impulse. So just to put us back where we were of feeling this touch and the information being sent down the axon or the nerve fiber of that touch receptor so that it can communicate with this neuron down the line, and that neuron is going to receive information through its dendrites. That information is going to travel across the soma, the cell body, build up at the axon hillock. And because I am indeed feeling this touch, right, that neuron, we need to get that information to the brain, to really the higher level processing of the brain. And so that needs to send its information down its axon as well. Now, as we're talking about this electrical conduction that occurs down the axon, what we're going to look at, and we've started this a bit, is this electrical gradient that is, there's a difference in the electrical voltage inside of that cell than outside of that cell. And I think I've shown this now with the meters, and we're measuring the difference. We're at -70 millivolts. That electrical gradient, where we are at negative 70 millivolts, is also known as polarization. And I usually make this comparison that I'm hoping helps. So 0 would be not at all polarized, and just like if we are in complete agreement, we are not at all polarized. But as I get down negative or I get up positive, the farther I get from 0, in the cases of talking to each other, the farther we get from agreement, the more polarized we are. The more negative we get or the more positive we get, those differences mean that there is polarization. So I'm going to go through a little bit of the physics of why what we saw in the last slideshow, why that's really happening. And the electrical gradient, so it's -70 millivolts inside the cell in comparison to outside the cell. And remember, our sodium ions are positively charged, our potassium ions are positively charged, and so that electrical gradient is working to pull the sodium ions into the cell, right? And it's working to pull both of those ions into the cell. For sodium, though, it's the electrical gradient and the concentration gradient that are pulling the sodium ions into the cell. So the differences in the difference in the distributions of those ions, that we have more sodium outside of the cell than inside of the cell. And if you know how diffusion works, we're going to kind of, if there's lots of a concentration of something, I'm going to move to where there's less. And just like we watch salt and sugar or whatever dissolve into water, it's going to go throughout the water. That concentration gradient is also pulling the sodium ions into the cell. So when those sodium channels open, when we get to our threshold of excitation, that sodium flows very quickly into the cell. Meanwhile, the electrical gradient is tending to pull the potassium ions into the cell, but the concentration gradient means that they are really slowly leaking out, carrying a positive charge with them. Those potassium channels can stay open, and because there's more potassium in the cell than out of the cell, that concentration gradient is kind of pulling those out. But the electrical gradient's pulling them in. So potassium doesn't have a lot of motivation, if you will, to move. If you also see in here, there are chloride ions in this picture at the bottom left that are negatively charged that I'm going to ignore because they don't move in all of this. And there are also anions. That's what that A negative is. And we have more of that, or we have those anions in the cell, but they're not going to be doing any of the movement. So I'm going to ignore those for now. Okay, so I'm repeating this picture because it makes sense to me to do this after I've just said that, where we get to our threshold of excitation, we're going to send this information down the axon, and if we're measuring, so if you remember, we have our reference electrode out there and our recording electrode where it can be affected by the axon or by this particular neuron. Sodium flows in, we go from -70 and flowing in, flowing in, flowing in. We go up to positive 40, and then those sodium channels snap shut. Potassium has been slowly leaking out, but it's really starting to flow out now, right? Because at positive 40 millivolts, both the concentration gradient and the electrical gradient are pushing that out. So potassium is flowing out and out and out, and we go back down to our negative 70 millivolts. And as I think most of the biological psychology textbooks say, we actually overshoot that just slightly and come back up to negative 70. And of course, if we moved that recording electrode down the axon, we would see this same thing happening just later in time. That is a propagated response that we're going to see from the beginning of the axon all the way through the axon until the end of the axon when we get to those terminal buttons. Okay, so as I walk through the action potential, I like to do that from the picture slides, but also to make sure I'm using the words and the terminology that I'm going to be using throughout and that you have these on a slide. So as we have been talking about, the resting potential is remaining stable until the neuron is stimulated, until it reaches its threshold of excitation. It's at negative 70 millivolts. We can see this hyperpolarization, and we're going to discuss this more when we talk about synapses, where we are increasing the polarization or the difference between the electrical charges of the inside the neuron compared to outside the neuron. So inhibiting the probability that that neuron's going to fire. And we can see depolarization, so getting that, decreasing the polarization towards zero when we see excitatory information coming into the neuron. We're going to send the action potential if we reach a threshold of excitation, so some level above which any stimulation produces this massive depolarization. And I'm going to show that on the next slide here with a picture of, so if I'm starting at negative 70 millivolts, if you see in the picture, in this particular picture, the threshold of excitation is put at negative 65 millivolts. And again, some of this I'm going to discuss again when we talk about synapses, exactly how we get to this threshold of excitation, how we're getting excitatory information and inhibitory information. And we're receiving information from many, many neurons, potentially thousands of neurons. We're summing this up to see if we reach that threshold. Just so you know, I can't even remember now what your textbook uses. This particular textbook used negative 65 millivolts. My sensation and perception text used negative 55 millivolts. Those thresholds differ slightly, that estimate differs slightly, and it differs very slightly for different neurons. So I'm never going to ask you that specific number, but just so you know the concept of the threshold of excitation, if we get enough excitatory information and we depolarize and we get to this threshold, then the neuron produces this massive depolarization, where that's when those sodium channels open. It goes up to positive 40 millivolts. Sodium channels close. The potassium has been leaving the cell, but now with the sodium channels closed, the potassium's leaving, and we see the loss of those positive ions. We go down and down and down to negative 70 millivolts, and then potassium channels close as well. Okay, and I'm going to say some of this again with just slightly different language. And again, now I feel like I know I'm repeating, but I want to make sure I have my terminology in there. And I want to refer to this idea of permeability, or really selective permeability, that the membrane is going to become selectively permeable to different ions depending on what's going on. So that stimulation, getting to the threshold of excitation, causes the channels in the membrane to become selectively permeable to sodium. And we've talked about how and why. Now that's going to flow in. And those are voltage gated or voltage activated channels, which means I needed to get to that threshold, that particular voltage, for me to open up those sodium channels. So now positively charged sodium ions flow in. There is that shift in electrical charge. We're going to go up and up and up to positive 40 millivolts. After the action potential occurs, sodium channels are quickly closed. The neuron is returned to its resting state because those potassium ions are able to flow out, because now the concentration gradient is letting them flow out, taking their positive charge with them. We go down past negative 70 millivolts just a bit, potassium channels close. And the sodium potassium pump, which I think I showed a picture of in the last slideshow, but now that I have the words here, that's going to restore those ions to their original distribution so that we can let this happen again. Okay, and here's where I usually ask for questions, but do think about what are your questions and if all of this is gelling and making sense and coming together for you. And so in that process of the sodium potassium pump, restoring those ion concentrations to their original distributions, that takes time. So if we get this unusually rapid series of action potentials, it can lead to a buildup of sodium within the axon, and that can be toxic to a cell. This really only occurs in rare instances when we're bombarding a cell, like in the case of a stroke, and especially a hemorrhage, where we're getting lots of blood into an area, and those cells are being stimulated again and again and again, and so they have this toxic buildup of sodium. It also can happen after the use of certain drugs. Okay, and importantly in all of this, which I've stated before, but without the terminology of the all or none law itself, the all or none law in this is stating that the amplitude and the velocity of the action potential are independent of the intensity of the stimulus that initiated it. What I mean by that is that, again, is going to start at that axon hillock. It's going to travel down the axon always at the same velocity, and it's always going to go in the examples I've been giving from negative 70 millivolts to positive 40 millivolts. So slightly different for different cells, but for a particular cell, that action potential is always going to be the same. It's always going to be the same velocity, always be the same amplitude. And so what this is showing, because I did say this before, but I liked this picture a lot from the Laura Freeberg. If we have the stimulating electrode, is that little pink thing, okay? And I have various recording electrodes now, or what she's marked here, amplifiers. What we see is if we're looking across time on my x-axis, that at that first amplifier, we're going to see that action potential earlier, but it's going to look exactly the same. If we go down, farther down the neuron, we have a second amplifier. We're going to see the same exact action potential, just later in time. We go to C, to another amplifier, we're going to see that same exact action potential just later in time. So that's the all or none law. And it's going to do that until it gets down to those terminal buttons, or the synaptic terminals. So if a neuron receives a signal that is of sufficient strength, it fires. If the signal is too weak, it does not fire. So it's just this propagated response. Once it's triggered, it's going to fire to the end. It does not decrease in size, same velocity, same amplitude. And although we have this all or none law, although the action potential itself is all or none, neurons convey information about stimulus strength. So whether it's a dim light or a bright light or a small sound or a loud sound, they do that by varying the rate at which they fire those action potentials. So I'm going to give an example of this with one of my favorite slides. So this is difficult to do online. I'm used to doing this in front of a class, and even then it's a little bit tricky. So I'm going to go across time. And just so you notice that, it makes sense, hopefully, that before when we went from negative 70 millivolts up to positive 40 and down to negative 70, and that was happening across time, we're going to squash that time. So now that's just a line on this screen. So each of those lines in A is an action potential, and we're watching this across time. And just so, if you want to do this thing where you just maybe lightly take your right finger or whatever and put just a little touch on your left wrist. Okay, wait to do that. So right now, your left wrist has spontaneous firing, and we can see that happening through time, where it's this time, fire, real slow. Okay, now if you touch your wrist real lightly, like in A, fire, 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 take it off, fire, fire. Okay, that's when those are the action potentials firing, coming from that touch receptor on your wrist. Now in B, now you're going to do this with a little more pressure. You're not just lightly touching, you're putting some pressure on your wrist. Okay, wait for it because we're going to have to, at first, the spontaneous firing, so there's no pressure on, there's just this time going. Fire, fire, pressure on, little harder pressure. Fire, 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 off. Fire, fire. One thing I like about this picture is that it does show that spontaneous firing, that we're not feeling anything when there still is this spontaneous firing. Neurons are going to fire every once in a while. It's when there's a more rapid rate of firing that we start to feel something. Now, I used to do this, well, if you're getting an Indian sunburn, but really that would be maybe pain. So maybe just grab onto your wrist really strongly when I say pressure on. Okay, so in C, we have the spontaneous rate, fire, across time, fire, pressure on, grab your wrist really hard, fire, 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 like Beavis and Butthead, right? Like fire, 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 fire. It's firing really quickly now to tell you that this is a stronger intensity. And we, of course, take it off and we go back to the spontaneous rate. So I'm hoping that made sense over the internet. Okay, and after an action potential has taken place, a neuron is going to have a refractory period. So that fire, 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 that really quick, that can only happen so quickly. It can't happen any faster than a neuron can possibly respond, because the neurons do have this refractory period. During this time, the neuron really resists the production of another action potential. And it does have an absolute refractory period and a relative refractory period, where the absolute refractory period is this first part of the period where the membrane really cannot produce another action potential. Those sodium channels have shut and they need to stay shut for some amount of time. The relative refractory period is the second part of this, where it just takes a stronger than usual stimulus to trigger an action potential, which this is how we get into that potentially having damage, because this relative refractory period allows those neurons to fire really too quickly for themselves. If there's a kind of a stroke or some kind of constant stimulation. I have heard this compared. I don't love the analogy because it's kind of ugly, but it works. I have heard the comparison of thinking about flushing the toilet. So if you flush the toilet, you have to wait some amount of time before you can flush the toilet again. I don't love it, but it works. Just so this is conceptualized to some extent, again, that this is happening all the way down the axon. We have in one place, so at the very beginning of the axon, sodium flows in and potassium flows out. We're going to have this voltage change, which causes this next part of the axon to allow sodium to flow in, potassium to flow out. This change in voltage, which allows the next part of the axon to let sodium flow in, potassium flow out. That propagation is occurring all the way down the axon. We also have the myelin sheath, which is playing a pretty important role of providing this insulating material. Again, these are the oligodendrocytes, those particular glial cells that make up the myelin sheath, that are made up of fats and proteins. And the myelin sheath, they wrap around the axons, but they really have these short, unmyelinated sections that are, you might say, interrupting them, called the nodes of Ranvier. And what we've been talking about now, if we have myelin sheath on our axons, this sodium flowing in and potassium flowing out and those channels being there, that's really happening at the nodes of Ranvier. So at each node of Ranvier, the action potential is regenerated by a chain of these positively charged ions being pushed along by the previous segment. So I'm going to do this with the picture because I like the pictures so much more. I'm going to start with actually the one in yellow. And again, these come from Laura Freeberg. I thought some of her pictures were really helpful. And I have the stimulation over on the left at 1. I get enough stimulation so that we see this action potential, sodium flowing in, potassium flowing out. And we also see, so those sodium ions, if you look underneath the myelin sheath now, that little darker part that's showing us the myelin sheath, you can almost think of this as someone turning on a hose, that they go sort of flooding down that area where the myelin sheath is there. And we're looking at this as time is now kind of occurring as we move downward. As we move down 2 milliseconds after the stimulus at that second node of Ranvier, now that one's going to have sodium flow in, potassium flow out. Those sodium ions are going to flow down the myelin sheath quite quickly. So again, it's allowing for this more efficient communication because it's like turning on this hose and just whoosh, those ions flow down so that we get to our voltage change that we need. Sodium flows in, we go down to number 4 there, 3 milliseconds after the stimulus, sodium flows in, potassium flows out, and that's happening quite quickly. And this myelin sheath, while also protecting the neuron and keeping it from that axon, keeping it from confusing its information with its neighboring axons because it's kind of insulated from them, it is allowing for much quicker communication, because if we look what's happening over in the green, this is showing conduction in an unmyelinated neuron. So some of our kind of dull pain, or neurons that are telling us about dull pain coming from whatever, maybe if I have it in my lower back, for example, that's coming up from my lower back, this kind of dull pain. It's unmyelinated, and you can see this pain is happening at the beginning. I get enough stimulus, sodium flows in, potassium flows out 1 millisecond after, go down to number 3, 2 milliseconds after, sodium flowing in, potassium flowing out. You can see how much slower that's going to be because we don't have that kind of like turning on a hose of really this kind of flowing down very quickly of those sodium ions. Again, I'm hoping all this makes sense as I'm talking over online and you're watching these. So do think about asking questions if some of this feels like it's not making sense. And the aspect of having the myelin sheath, this is referred to as saltatory conduction. So salta is the beginning of, it's Latin for something like jumping, and it is used to describe this jumping action of the action potential from node to node, that kind of flowing through very quickly underneath that myelin sheath. This really conserves energy for the cell, as we see that sodium-potassium pump and the changing of the channels and all that takes energy, and it provides much more rapid conduction of impulses, which I showed on the last slide. And just so you know how important some of this is, so we build up that myelin as we have our neural system developing. And people who have multiple sclerosis, they have an autoimmune system where they have a disease where their autoimmune system is attacking those oligodendrocytes, and so the myelin sheath is destroyed. And for the unmyelinated axons, that's okay because we have those sodium and potassium channels and everything we need all along the axon. But where that myelin sheath was originally put around those axons, those sodium and potassium channels don't exist. So it's really not allowing for the communication and especially for neurons that have to communicate longer distances. So this is associated with poor muscle coordination, sometimes visual impairments. At the very end of this slideshow, I'm going to come back to this original picture, which again now I've put up here a few times to hopefully encourage you to think about questions. But so this communication in the nervous system, I'm feeling some kind of touch, some kind of stimulus from the environment. My touch receptor is going to get enough stimulation since I'm actually perceiving this. It's going to reach its threshold, send that action potential, which we've been talking about, down its nerve fiber. That's going to be propagated all the way down the axon, reaching those synaptic terminals or terminal buttons. And then we're going to release a chemical or chemicals to communicate to the neurons down the line. And again, because I'm feeling this touch, I'm getting that postsynaptic neuron is receiving excitatory information, enough so that it reaches its threshold of excitation and sends its information down its axon so that we can feel this touch on our wrist or our hand or whatever. This is, again, really simplistic as we're sending from one neuron to one neuron, looking like it might be communicating onto one neuron, but honestly, this is happening in the brain oftentimes with that postsynaptic neuron is receiving information from thousands of other neurons. As we're going to talk about when we get to the synapses, this can be excitatory or inhibitory. And I'm going to then be sending my information on as the postsynaptic neuron, again, to maybe hundreds, maybe thousands of neurons. It really depends on the neuron. So this gets really complicated. But just so we have this really nice, simple way to talk about it, it's a nice ending slide. And again, think about questions that you have so that when we move on to synapses and communicating between neurons, this all makes sense. And so this runs a little bit longer than my regular 25 minutes. But I realized, hey, I think I'm a little bit ahead, which I'm suspicious of, but it's all good. So this is a Friday, and think about questions for Monday.